All right, let's start. So, last time we discussed this theorem 7. So, this chapter is about linear dependence or independence. So, we say, so given a set of vectors, so we are initially given a set of vector from V1 through Vp, and then the question is whether they are linearly independent or dependent, okay? And then basically the meaning is when we construct this vector equation where this P part is all 0, if we can find a non-trivial solution, so for those linear combination coefficients, at least one of them is non-zero, so that's what we call non-trivial solution, because when they are all 0, it will become trivially true, right? So if we can find a solution for those linear combination coefficients where at least one of them is non-zero, and then we can, in that case, we can find a non-trivial solution, and when we can, in this case, we call these vectors as linearly dependent, okay? But on the other hand, if we can, the only solution that we can find is all zeros, and then we call them as a linearly dependent, okay? Okay, and then this theorem 7 is saying that suppose we have maybe 4 vectors that are initially given, okay? If they are linearly dependent, okay, which means for those small rectangles, at least one of them is non-zero. That makes this equation as true. In that case, it is equivalent. I mean, mathematically, this case is equivalent to the case that for at least one vector. So there exists at least one vector. Suppose that vector was, for example, V2. Okay. We don't know which vector it is, but at least one vector is represented as linear combination of the other. So we have 3 remaining vectors, V1, V3, and V4. And then we consider the linear combination of them. And then this equation, we can always find this relationship at least for at least one vector among the vectors that we have. So if you check the differences between them, in the previous case, it was originally homogeneous linear system or homogeneous equation because this part is 0. But in this case, between the equality sign on the left-hand side, we see one single vector that doesn't have any linear combination coefficient. In other words, in this place, we have to always make it as 1, right? So that's when we call this V2 as linear combination of the other. Okay? So basically this theorem 7 is saying that those two cases are the same. I mean mathematically equivalent. So if those 4 vectors are linearly dependent, and then for at least one vector, we should be able to find this equation. And then if we can find this kind of equation for at least one vector, we don't know which vector it is, but if we can find this equation, and then it is always the same as the fact that they are linearly dependent, which means we can always find some non-zero solution or non-trivial solution for those linear combination coefficients. Okay? And then the intuition is really simple. So for those 4 values, at least one of them is non-zero. So that is the definition of non-trivial solution, right? And suppose that non-zero value was this guy, okay? So we don't know those values, but at least we know this value is non-zero, because that's the definition of a non-trivial solution. And then suppose that value was maybe 2, okay? We don't know this value, but we know that is certainly non-zero. And then how we make the second equation using the first equation is really simple. For this guy that has a non-zero coefficient, we just simply move it to left and then move the other part to right, okay? And then those 3 values will just be the same as those values, okay? And then we just moved this guy into here, and then since we know this value is non-zero, we can simply divide each side by that non-zero value, so that we obtain this this coefficient value as 1. Okay, so that's why those 2 are mathematically equivalent. Okay. Okay, and then the second part in this theorem is saying that, okay, and then let's try to find this relationship. So for some vector, suppose we want to find its linear combination representation using the other vectors. Okay, in that case, in principle or by default, we have to consider all the remaining vectors. So if we had originally 100 vectors, and then for one vector, the linear combination of the other means we have to involve all the remaining 99 vectors, right? Which is quite cumbersome. I mean, it may take a lot of time to write 99 vectors at a time. Okay, so again, the purpose is to find at least one relationship in order to say that these 4 vectors are linearly dependent. And then how we can find this equation is as follows. So if we have 4 vectors, and then we try to find the linear dependence relationship by only using one vector. Okay. And then if we cannot find the relationship for this first vector, and then we move on to the second vector, and then we try to represent, we put this guy to the place here, and then we only use the vector on the left side, which we only have just, where we only have just one vector, right? Okay, and then if we cannot find this linear dependence relationship or this linear combination representation for this vector, and then we now move on for the second vector. The third vector, and then we try to find this relationship by only using those 2 previous vectors. Okay, so that way we can kind of avoid having to handle all the vectors, all the 100 different vectors. Okay, So if we get lucky, out of 100 vectors, at maybe 11th vector, this vector might be represented as a linear combination of the previous 10 vectors, okay? Which means the 10th vector is, 11th vector is represented as a linear combination of the previous 10 vectors. Okay, so so that's how we find the linear dependence relationship in practice. Okay, so at some point, if we can find this relationship, and then that's when we can just stop and then conclude that they are linearly dependent. Okay. Okay, so yeah, let me explain why this is true. So why we need, this kind of a process of finding this linear combination relationship sequentially by using only the previous vector. I mean, why should it be true, or why should it be the same as this linear dependence relationship that we just learned? So in the previous case, I mean, in this second equation, this vector should be able to, in principle, we have to use all the remaining vectors, all the 99 vectors, right? But in the third case, I'm just saying that for one vector, we don't know which one it is, but we have to be able to find the linear combination using only the previous ones, right? So let's try to understand why these two cases are equivalent, okay? So that is really simple. So suppose there exists some linear dependence relationships for maybe 100 vectors. And then the original definition of linear dependence is that for this homogeneous linear system, which has V1, V2, maybe V, suppose that is V41, for example, and then all the way up to V100, okay? And then we know if they are linearly dependent, at least one of these coefficients should be non-zero, okay? So at least one is non-zero, but we may have multiple non-zeros, right? So this guy may be non-zero, maybe it's -1, and then in the place of V5, that is also non-zero of 2, okay? And so we just consider all these non-zero values, and then our assumption here is that this guy, the linear combination coefficient corresponding to this V41 is actually the last non-zero entry, okay? And then the remaining part is all 0. So that is our assumption, okay? Yeah, in the worst case, the last non-zero entry could be just the actual last entry, okay? But sometimes it might be, the last non-zero entry might be corresponding to much earlier vectors. For example, V41, okay? So in these cases, suppose, just in this example, suppose this V41 has the last non-zero coefficient in this non-trivial solution, okay? And then we know from our assumption, we know all the coefficients after V41 will become 0, right? And then it means, so how did we move from the first to second? If we know one of them is non-zero, and then we just simply move it to the left, and then the remaining ones to the right. And then we just simply divide it by this non-zero value, right? So that's why we can, we can do the same thing. So this is the last non-zero, and so we move this value and V41, and then yeah, originally we will have a V1 through V40 and then V42 all the way up to V100, right? But because we assume that all the coefficients after 41 is 0. So all the coefficients after 41 are 0 because 41 was the last non-zero entry. Okay? So we can safely ignore them. Okay? So we can definitely ignore them because we know, or from our assumption, we know these parts are having all 0 coefficients. Okay, and then this guy will give us the representation of V41 by dividing this non-zero values on each side, and then we now have a linear combination representation for this guy, V41, by using the previous vector from V1 through V40. Okay? So that's why this kind of sequential finding of a linear combination representation is equivalent to this, the second one. Any questions? Okay, then let's look at the simple example where we can apply, or where we can utilize this theorem that just we learned. So suppose we are initially given these two vectors in three-dimensional space. So this is u and v, and then the question is, so when we consider another vector w, okay, so we consider another vector in three-dimensional space, and then so in this example, it's saying that if u, v, and w, although we do not know yet exactly what this w is, but if u, v, and w are linearly dependent, and then it is the same as the case that this w should be linear combination of these two, u and v. Okay, so that's when those three vectors u, v, and w are linearly dependent. Okay, so let's see why. So we are initially given three vectors, and then we apply this third, this kind of trick. So we consider only one vector and if it's linearly dependent or not. So when considering only one vector, if it is linearly dependent, there exists only one case where this vector is what? So you are given only one vector, and this vector is linearly dependent. And when is this vector linearly dependent? Okay, so let me try to simplify the question. So this is one three-dimensional vector where we have three entries, and we are only given just this vector. And what kind of vector will be linearly dependent? We are given only one vector, and then when is this set? Span of what? Oh, so yeah, we are considering a much simpler case. We are only given just a single vector, only one vector. Okay. Last row is 0. Last row. Yeah. So regardless of this example, we only think about just a single vector, and then our entire vector set is containing only just that vector, only one vector. And when is this linearly dependent? When? 0, right? So when this vector is completely 0, and then this vector is linearly dependent, right? And why? This is the example that we discussed last time. So we have three vectors which we do not know, and then this homogeneous vector equation should have non-trivial solution, but we only have just one linear combination coefficient. That should be non-zero, right? And then suppose this value was 2, and then it makes each of our entry now in the vector be all 0, right? So that's so that way, if one vector is linearly dependent, and then that's when this vector is just the origin or all 0 vector. Okay, so back to this example. We started from only considering just a single vector u, and then this is not a 0 vector. So this is up to this point that is linearly independent. And then we move on, and then consider the second vector. Okay, and then in this case we have to consider if it's possible to represent this second vector as a linear combination of the previous vector, where we only have just one vector. In that case, are they linearly independent or dependent? So in the case of these two vectors, when the second vector is along the line of the first vector, that's when they are linearly independent. That's when they are linearly dependent. Okay, but this clearly is not, right? So it's like having the ratio of 1/3, and this one has the ratio of 6. So it's already not in the same line. Okay, so up to these two vectors, they are linearly independent. Okay, and then we now consider another vector w, and then when these three vectors are linearly dependent. So if three vectors are linearly dependent, because we checked until the second vector, and then they were linearly independent up to that point, and then the last remaining case should be linearly dependent, which means the last vector should be represented as a linear combination of these two, right? So that's the only case that makes these three vectors as a linearly dependent. Okay, so in other words, this vector w, the third vector should be belonging to the span of the first two, which means the last vector is represented as a linear combination of the other two. Okay, so that's when those three vectors are linearly dependent. Okay? Okay, and then let's move on to the next theorem, which is theorem 8. But this is quite simple. So there exist two numbers, two scalar values that we kind of consider or care in this case, which are p and n. So we consider the vector living in Rn. So suppose Rn was maybe 4, and then we consider 4-dimensional space, and then in this 4-dimensional space we are given p vectors. The number of vectors is p. In that case, if p is bigger than 4, so that is this guy, p is greater than n, in that case, regardless of what these vectors are, they are automatically linearly dependent. Okay? So again, let's think about the example. So we consider 4-dimensional vector, but we are given 5 vectors living in 4-dimensional vector space. So again, we are considering a 4-dimensional space, but we are initially given 5 vectors in this 4-dimensional space, and then they are automatically linearly dependent. Okay, so that's what this theorem says. And then, yeah, let's think about a simpler case. So in this three-dimensional space, suppose n was 3. So we are considering this kind of three-dimensional space. And then I'm going to give you 4 vectors. So one vector, the first, second, and third, and then the other fourth vector. Okay? So I'm going to give you this 4 vectors in this three-dimensional space. And then you guys know those 4 vectors are automatically linearly dependent. Okay? Because, yeah, you can think of this, yeah, you can understand this theorem by applying the previous theorem. So we add one vector at a time. So we added one vector. I mean, let's try to make this case as linearly independent because they are all, yeah, they are saying it should be always linearly dependent. So let's try to find some counter example. So we start with one vector, and then the second vector, which are still linearly independent, right? And then the third vector. And if the third vector is inside of the span, and then yeah, it's a bad case where these 3 vectors are linearly dependent, but we can still make this vector not belonging to the plane, which makes these 3 vectors are linearly independent. But if you consider the span of these 3 vectors, okay, span of these 3 linearly independent vectors, and then they already covered the entire space. So their span, the span of these 3 vectors are now representing any points in the space. Okay? And then when adding the fourth vector, regardless of what this vector is, that vector should be always represented as a linear combination of these 3, because the span of 3 vectors are covering up the entire space. Okay. And also, this theorem can be also understood in terms of free variable and pivots and reduced echelon form and so on. Okay, so in three-dimensional space, let's consider the same case. And then we have 4 vectors in three-dimensional space. In that case, in order to find whether they are linearly dependent or independent, we construct the homogeneous vector equation, right? And then set it as 0, and then see if we can find some non-zero solution. And then this guy is the same as this vector equation, right? So we have 3 rows because they are living in 3-dimensional space, and then 4 columns, right? And then this matrix A times X equals 0. When does this equation have non-trivial solution? This is when they have free variable, right? And what was the free variable? So the free variable is some column, okay, some column that doesn't have any pivot. So in this case, we only have 3 rows, and then we only have just 1 pivot per 1 row, right? We cannot have 2 or more pivots in the same row, right? Because the first non-zero entry per row, that is the definition of a pivot. Although this form should be first converted into echelon form, right? So we have like 3 cards, okay, that we can use, and then we can assign each of these 3 cards to 4 variables, right? And then automatically one of our 4 variable cannot have 1 card, right? Because we can have maximally 3 pivots at most, but we have a 4 variable. So at least 1 variable should be the free variable. So that's, we can understand this theorem by looking at the shape of this matrix. Questions? Okay. And then now, let's think about the opposite case. What if we have maybe two vectors in three-dimensional space? So we are given p number of vectors, where p is only 2, but they are living in three-dimensional space. So now the number of vectors is less than the number of dimensions. So in this case, can we say those two vectors are linearly independent or dependent? Okay. So the question is, I will give you these two vectors in three-dimensional space. So are they always linearly independent, or are they always linearly dependent? So the question is, in this shape, where we have only two vectors in three-dimensional space, in this case, yeah, are they always linearly independent, or are they always linearly dependent? So the answer is, it actually depends. So it can be linearly independent, or it can be linearly dependent. So yeah, you guys know that when the two vectors are in this form, like this, and then they are linearly independent. But in the three-dimensional space, if this guy is coinciding with the first line, and then that's when those two vectors are linearly dependent, right? So when the number of vectors is smaller than the dimension of the space, yeah, we cannot say, before looking at the actual vectors, we cannot say they are linearly independent or dependent. Okay, then this is the last theorem in this chapter. So the last theorem is a quite simple one. So if we are given this p number of vectors, and then if we know one of this vector is a completely zero vector, and then this set is always linearly dependent. Okay, so that is this theorem. So we know that when we have only one vector, and when that vector is a zero vector, and then we know that vector only will already be linearly dependent. Okay, but even when we have a more number of vectors containing still this zero vector, and then they will be still linearly dependent. And that is really simple. Suppose we have 100 different vectors, okay, and then maybe V41 is a completely zero vector, and then we have to find the solution for those linear combination coefficients where at least one of them is non-zero. Okay, and then I can immediately find one such solution by the fact that this 41 V41 is 0. What would be the solution for it? Okay, I'll give you bonus point for the student that give an answer for this question. So the situation is, we are given 100 vectors, and we know one of the vector. For example, suppose that vector is a V41, and then that is a completely zero vector. And in this case, what would be the solution? I mean, what would be the non-trivial solution that satisfies this equation? In other words, how can we set those linear combination coefficients to make this equation as 0? I mean, this equation to be true. Right. Yeah, right. You did? Okay, yeah. I'll remember both of you guys. Okay, so we don't know the other vectors, okay? So we simply set all of these 0 except for this guy, okay? But this guy is a 0 vector, so yeah, it doesn't matter even if we just multiply it with, for example, 3 here. And then 3 times 0 vector is still 0. And so we know this guy is still be 0, right? But that will become at least one non-trivial solution, because the definition of non-trivial solution is that at least one of them is non-zero. Okay, that's the only requirement that we have to satisfy. Okay. Okay, so among our vectors that we are given, if it contains 0 vector, and then we don't need to bother at all. We can immediately conclude that they are linearly dependent. Any questions? Okay, and so that's it for chapter 1.7, and we now move on to chapter 1.8. Okay. Yeah, let's call the attendance. 네, 이훈익. 네. 이훈익. Are you? Okay. 김태경. 이상진. 박상유. 알무자이니. Okay. 사동회. 최병록. 디달. 김홍우, 정재현, 김현학, 아칸시, 디브컬, 아칸시, 홍석민, 김건희, 김호석, 김수연, 강준원, 조현재, 있어보자. 배정인, 곽성원, Okay, so this is a new weight. So we see the 2 students having the highest probability of being selected the next time. Okay, and then chapter 1.8 is about linear transformation. Okay, so in this chapter, we study something called a transformation, or basically a function. Okay, so we consider a function that maps some input into some output, and our input and output is a vector, because we are studying the linear algebra, and so we mainly use a vector as a form of an input and output. So you guys know what the function is. So when I studied in my elementary school, this kind of box was function. So suppose this guy. So I'm gonna put the 3 into this box, and then this box will give 9, right? So this is a function output when using 3 as an input. Okay. So what about giving some vector 1, 2, 0. I will put this vector as an input to this function, and then it will give some function of 3, 2. Okay, it can give some vector in different dimensions. Okay, and then a sneak peek about this chapter and the next chapter is that this function is actually represented as matrix, and this matrix A is now defining our function, so that when this vector is x and this vector is y, and then y is defined as a times x. Okay, so when talking about our matrix, previously we considered the matrix A as like a coefficient matrix or augmented matrix starting from our linear system or set of equations. But now we consider the matrix A as some kind of function operator. Okay, so in this case, what is the size of an A? So what is the size of an A? The matrix A, 1, 2, 3, 1, 2, 0, some matrix, and then that will give 3, 2 as an output. What should be the size of the matrix A? So let me make it as a the multiple choice. So 3 by 3 or 3 by 2, 2 by 3, 2 by 2. It should be 2 by 3, right? So that way when the matrix has the size of 2 by 3, we don't know those values yet, but at least we know the shape of this matrix or the size of a matrix, because it will multiply itself with the 3-dimensional vector, and then as an output it will give 2-dimensional vector, right? Okay. So let's go through some some terms defined in this transformation or function or mapping. All the 3 terms are having the same meaning. And then so the first term or first keyword that we learn is domain and the codomain and the image and the range. Okay, so let me ask the question of what is the Korean term in this each of this word? Domain. What is it called in Korean? Domain in function. Okay. What about codomain? So you'll be similar, related to y, but the y had 2 different sets. 그죠? 공역과 치역이 있었죠. So codomain means 치역일까요? 공역일까요? 공역, 치역. 네, 공역. 다음에 이 둘 중에. So between the remaining 2, what will be 치역? Image or range? So this is a 치역. Okay, and then this is called so this is the meaning of it is something like this: function value or function output. Okay. Okay. So in this example, although we don't know the exact matrix A, but we know when using x as this vector, we get this output from this function mapping, right? So this vector 3, 2 is called image, okay, of a vector, input vector of 1, 2, and 0, okay, through our matrix A. Okay. Okay, and then in this shape, in this matrix shape of 2 by 3, so you guys know the input vectors are living in 3-dimensional space. So if we consider all the possible 3-dimensional vectors, then that is called this R3, right? And then this becomes our what? Among domain, codomain, image, and range, what will be R3? Okay? It's domain, right? Because it's the corresponding to X input vector, right? So the space, the entire space that this input vector is living in is called domain, right? Or 정의역. And then what about the this codomain? So codomain is the entire space where this 2-dimensional function output vector is living in. So R2 is codomain in this case. Okay. Okay, and then what is range? So here range, which is a 치역. So this is basically a subset of 공역, right? And so our 치역 or our range is the subset of this codomain of a 2-dimensional space, right? And then, yeah. So this R2 is basically a subset. I mean, the range is basically a subset of R2, and then this range is understood. I mean, you can understand what the range is in the case of 1, 3, 2, 1, and 4, minus 1. So suppose we are given this matrix A, and then what is the range of this matrix transformation? Which means when using any vector here, okay, by just multiplying it with the A, and then we collect all the possible y values, right? And then collecting these y's, and then we form range, right? And this range is basically the span of those 3 vectors, right? And why? So you know this matrix and vector multiplication is the same as vector equation form of x1, x2, x3, and then 1, 3, and 2, 1, 4 minus 1, and x1 plus x2, x3 as a linear combination coefficient. So we change x1, x2, x3. Yeah, we freely change those x1, x2, and x3, right? And then we collect all the possible answers or all the possible outputs that has this form, right? So that is basically defined as the span, right? So that is the same as the span of these three vectors, right? Okay, so basically when using matrix A as our function transformation, and then the range is the span of these columns in our A. Okay. Let's look at the example then. So suppose we are given A here, and U as a two-dimensional space, two-dimensional vector, and B as three-dimensional vector. So we now have 3 by 2 matrix. So in this case, what is a domain? Is domain R2 or R3? What is domain between these two? R2 or 3? R3, because the input vector R2 or R3? 2. 3. Yeah, it should be 3 because no, it should be 2, right? Yeah, I just followed the wisdom of crowd, and I just followed the majority. But yeah, when matrix A is defined in this form, what should be the dimension of the vector that is multiplied on the right? It should be two-dimensional vector, right? So that's when this matrix vector multiplication is defined, right? So domain is R2. And then what about the output? The output vector is living in R what? 3. Because suppose I gave 1, 2 as an input, and then you guys can compute A times X as this kind of three-dimensional vector, right? So our codomain or 공역 is R3, right? And then what about the range? The range is a subset of R3, but that range is linear combination, the span of these two column vectors in A, right? So that's what we learned in the previous slide. Okay, so we are given these 4 questions. So the first question is find T of U, which means when using matrix A as our transformation, what is the image or function output value of U? So we plug this U 2, minus 1 in the place of an X part, and then we simply compute X times U, right? So the output can be easily computed. So we have an A, and then we have an X here, U here, and then the computed output will be the image of this input vector U, right? Okay, then the second question is a little bit difficult. So find an X whose image under our transformation is B. So it means this. So A times X equals B. Okay, so we don't know the vector X, but we know its image after transforming it through matrix A. That vector B is known as 3, 2, minus 5. So this is our function output. And so the question is, what will be the vector X that satisfies this? Okay. And this guy is, yeah, this guy is nothing but just a matrix equation that we are quite familiar with, right? So the second question is just the same as solving this linear system or this matrix equation, right? So again, A and B is given, and then we have to find the X that satisfies this equation. Okay, so this is that form. A and B here, which are known, and then we have to find out X here. Then the remaining story is the same. We do this row reduced echelon form, and then find out the solution. Okay, then the next question is there more than one X whose image under T is B? So the question is still the same. So we consider this setting. Okay, this setting, A and B is given, and X is an unknown. And then the this question is whether we have only one x or there exists more than one x. Okay, and so this guy is the same as asking whether we have a multiple solution for x satisfying this equation or only one solution x. Okay, so that, yeah, that is a yeah, that becomes obvious because from looking at this reduced echelon form, so this is our coefficient. So in this case, how do we determine whether we have a multiple solution or only one solution or no solution, right? So the first step, I mean, it's just a review. The first step is to find whether we have a all zeros and non-zero, except for the last entry. But we do not find such rows, right? So we now know we at least have a one solution or infinitely many solution, right? And then the next thing to check is to whether we have a free variable or not. So we have two variables, O1, x1 and x2, and so both of these variables are basic variables, and thus we know there exists only one solution in this case, right? So for the answer of this question will be no, because we have only one solution. So the third question is the same as checking whether we have a solution and then whether we have a free variable or not. Okay, and then the next question, which is the last one, is, so we are given A, and then now we are given another vector C, okay, in the place of this B. And the question is whether this vector C is in the range of this transformation X, which means for this given C, okay, so suppose C, okay, so let's look at the solution. This C was 3, 2, 5, okay, and then the question is, can we find at least one x satisfying this equation, right? So this is nothing but another linear system, right? So in this case, after converting it to reduced echelon form, we now have this, right? So we have 0, 0, except for the last non-zero entry, and thus we know this one doesn't have any solution. So in this case, this, we know, from the function, from our understanding about the function, by viewing this matrix A as a transformation, okay, the range of this transformation or the range of this function or 치역이죠. This range of transformation A doesn't contain C. Okay, so C is basically outside of our 치역 or the range. Yeah, alpha. Yeah. Okay, then so the next slide is about this shear transformation, but personally I don't think it's that much important. So let's skip a few and then directly go to the definition of linear transformation. So transformation or mapping or function, a particular function can be either linear or non-linear. Okay, so among so many functions, they are split into two categories depending on their depending on whether they are linear or non-linear. And then let's look at the condition or requirement so that they can be linear transformation. So in order for a particular transformation to be linear, they have to satisfy these two conditions. So we are given two input vector initially, u and v, and then it is like this. So we consider the image or function output of this input vector u and function output of v, and then we consider their addition, their summation between these two function outputs. That function output is the same as just adding these two input vector first, and then later on we give it to this function to obtain the output. Okay, then the next entry is we are given some input vector u, and then we consider it's a scalar multiple. So if we are given maybe 3, 2, 1 as an input vector, and then suppose the output of this input vector was 1, 2, and we consider the scalar multiple. For example, suppose we multiply this vector by 2, and then the vector is 6, 4, 2. Okay, and so if we give this 6, 4, 2 as an input vector, if the output was 2, 4, which is exactly 2 times of our output of the first vector, and then that is satisfying this second condition. Okay, so let's try to understand, although it's just quite simple, but let's understand it using this box representation. Okay, so let's just simplify the case so that we just consider the scalar values as a function input and output. So we don't know what this is doing, but suppose you know when giving 2 as an input and output was 5, and then maybe 3 as an input, and then the output was given as 7. Okay, and then the first requirement is saying that, okay, so you have this function mapping relationship, and what if you add these two first, 2 and 3, which is 5, and then what if we give this 5 as an input to this function, and then the result should be what? The result should be the addition of these two individual function output. So it should be 12. So this function is satisfying this kind of relationship for any of the two input values, or it can be input vector. Yeah, if it is always true, and then it's satisfying the first condition. And then what about the second condition? Second condition is like this. So we have originally this relationship of giving 2, and then we have 5 as a function output. And then what if I give 6, which is 3 times 2, right? And then automatically the output should be also 3 times of the original output, which is 15. Okay, so when giving 2 as an input, and if the output was 5, and then when giving 3 times of the original input, and then the output should be also 3 times the original output. Okay, so that is this second condition. So so for any of the input values or any of this scalar multiple value that we used here, we used 3 times of the original value here, right? So when freely changing this value or this input values, and if the two conditions shown here are always true, so if the two of these conditions are always true, and then that's when our transformation is linear. Okay, it's quite simple, right? Okay, and then using these two, by the fact that those two requirements should be always the same, regardless of any inputs and any scalar multiple C, we can obtain some interesting properties of this linear function. So that linear function has to satisfy this. So in this example, I only used just a scalar value, but it can be easily extended in the vector case when giving some vector 1, 2, and then we are receiving some vector, maybe 3, 2, 1, right? So this notion is easily extended in this vector case. So by using these two requirements, we can derive this fact, which means when giving, so we don't know this function, but when this function is satisfying the two conditions that we discussed, and then if we give 0, then we should always have 0. And let's see why. Okay, so we know we can freely choose these values. Okay, so suppose, okay, I'm gonna draw this box again. And then, let's just think about the case where we give 3 as an input, and then it gave the function output as 5. And then, what will be the function output when giving -3 this time? And then what should be the output? What should be the output? -5. And why? Why is it true? It's a scalar multiple, right? So -3 is scalar multiple of 3, right? By the factor of -1. So output should have also the same scalar multiple factor. Okay? Okay, so if we have 3, and if we have the function output of 3 at 5, then -3 will be mapped, or we'll have the function output of -5. And in this case, let's use the second rule. Let's utilize the first rule. Then what if we just add these two? It will always give 0, right? And then what should be the function output? The function output should be the addition of these two, right? Which has exactly like a relationship of -1, like a scalar multiple. So we can always have 0 output. So we always have a 0 output, right? So we utilized the two conditions here, and then although this one was just one example, but this one, you guys understand, this relationship should be always true for any linear, transformation. Okay, so in the case of vector case, if the domain was R3 and the codomain was R2, in that case, if our function is linear, and then if we give all 0 vector, and then the function output should be also the 0 vector by just simply extending it to a function case, right? I mean, the detail. Huh? There's not more than one function in the process. I mean, for any functions, we should always satisfy this condition. And yeah, it should be always true, regardless of any function, as long as it's linear. Okay, any linear function. And yeah, basically the linear transformation between the vectors, it is always defined as matrix vector multiplication. Okay, so again, you can, let's think about the transformation that maps a vector into another vector. Okay, so for example, like a domain is R3 and the codomain is R2, and this transformation is saying, this transformation is sending three-dimensional vector into some two-dimensional vector. And in this transformation, I didn't say this is, I didn't say anything about this transformation between the vectors, but if I say that transformation is satisfying these two, and then it is always the case that such kind of function is defined as matrix multiplication. Okay, so we will learn more details about why it should be true, but in this special case of matrix multiplication. So for example, for any matrix that you have, so if we have a 2 by 3, and then it is sending three-dimensional vector into two-dimensional vector, right? And then suppose we are given, or suppose we give a 0 vector to this function as an input. And then you guys don't know the exact value for this matrix, but you always know the function output. When multiplying some matrix A with the 0 vector, it will always become 0 vector, right? So that way, the transformation defined as this matrix multiplication is automatically satisfying this condition. Okay, and then let me ask some interesting, hopefully interesting question. Is this linear transformation or not? Is this linear or not? Linear. Non-linear. Okay, so in this case, we can view this transformation as a kind of a special case of transformation of a vector into a vector. But in this case, x is a scalar and y is also scalar, right? But scalar is still viewed as a special case of a vector, right? And so in this special case, if this transformation is linear, when giving 0 as an input, what should the output value be? It should be also 0. Right? But you guys know this guy is mapped into some non-zero value. So in this case, it's not a linear transformation. And also, again, I mentioned that linear transformation between vectors should be always defined as a matrix multiplication. So in this matrix multiplication case, we have a scalar and scalar, right? And then what is our A? What is the size of a matrix A? It's just scalar value. So that's when this matrix vector multiplication is defined in terms of the size. So A is nothing but another scalar, right? So if y is some value, some representation of this just a scalar multiple of original scalar value, that's the only case when this scalar to scalar transformation is linear. Okay, but you know this constant is existing, and so that's messing up this linear transformation. That makes it as a non-linear transformation. Okay, so that's it for today. Yeah, again, as you received the email, we will have a first midterm exam next Tuesday, right? And then also probably today we will have the new homework will be announced, which has the deadline on next Monday. Okay? Yeah.
Apparently, when you were checking the attendance today, I've been in the bathroom. So.
Okay.
I am not. Excuse me, but I am.
1 second. Yeah.
Okay.
Number 30.
Number 30. Okay.
I uploaded my homework at 12, maybe 35
괜찮아요,
a.m.
괜찮아요. 네, 괜찮아요.
Okay.
네, 괜찮아요. 그거 괜찮아요.
교수님, 저들이 이거 아까 졸다가 susceptibles.
네. 네. 그림이 어떻게 돼요?
이준이고 아까 6번.
6번?
오늘.
6번?
예.
아, 오늘은 안 불렀어요.
아까 저 보셨어요.
그래요?
네. 이건 오늘은 아닌 거예요. 오늘 아닌 거.
아, 근데 여기 이 6번이라고 그랬죠?
예, 6번에.
6번은 지금, 네, 출석은, 네, 미싱한 걸로 체크는 안 했는데.
그리고 도수.
네. 자, 해보죠. 한 번 했네요, 여기서.
아, 네.
네.
그러면 제 시간에 왔었는데 화장실 갔다 왔는데
이름이 뭐예요?
배정인.
배정인 몇 번인지 모르죠? 네. 잠깐만요. 아, 네. 오케이. 네.
With the MATLAB, I came to you, I was like, couldn't install it. But
You couldn't install it?
I eventually was able to install it.
What's that?
I said I was eventually able to install it.
Oh,
Like, I
okay.
was making a very silly mistake because it said write license and it put license in like quote. So I was just putting license there. And then you said I should use the school email and I did. But then until I went to the FTP and because like the school Wi-Fi is pretty bad, the FTP doesn't open. So like until when I went to the FTP from my place and then I saw that there was actually a license that the school issued for
So
us.
you're now good.
Yes, I did it, but then it was late to submit.
I
Actually.
see.
Yeah, I don't know if I can be able to get the regular marking.
Did you contact earlier me or my TAs about the difficulties?
Yes.
Oh, you did?
Yeah, I came to you.
Okay.
I told
So
you.
so you communicated via email with me or my TA, right?
No, after the class, I came to you and I told you.
You mean right now?
No, like last week.
Last week.
Before the deadline, and you said I should use my school email, which I
Right.
did, but
Right.
it was still like the same.
Okay. So when did you submit your homework? Like what time?
Like 3 days ago.
3 days ago. So I'll discuss with my TA.
Okay.
Okay.
Should I write my name on my?
Yeah. Can you send me an email?
Okay.
Describe it. Yeah.
Thank you.
For this sheet, I don't understand because there is more than one x which I need on the key.
Yeah, so basically, yeah, we consider the transformation which sends one vector to another vector, right? And then we are given the function output. And then the question is there any x or input vector that has the function output as this given vector? But here, more specifically, the question is, are there more than one possible, or are there more than one vectors that maps to the same given vector? Okay?
Somehow I do that.
Yeah, so, yeah. Let's see. So this is a function transformation x to b, right? So b is given as some constant vector, right? And then the question is whether we have only one x or multiple x that satisfies this equation. So in that case, if suppose b was 1, 2, 3, and then the possible x was 1 minus 1 and 2 minus 2, 0, and both of them are mapped to 1, 2, 3.
Okay, that's it. Okay, thank you very much.
저 이게 그
이게 리니어 디펜던트가 있고 어쨌든 요거를 하나를 그 리니어 컴비네이션을 해서 이 그 공간 안에 걸린다는 거잖아요.
네.
근데 이거는 그러면은 그냥 안 걸린다는 거 아닌가요? 이게 왜 이렇게 식을 썼는지.
네.
제가 이해가 안 되거든요.
일단 이게 그러니까 그 호모지니어스 리니어 시스템
네네네.
아니면
네.
이 벡터 이퀘이션으로 보고 b 파트가 0인 거죠.
네네.
그랬을 때 이거의 솔루션은 우리가 이제 무슨 벡터든 간에 이 그 리니어 컴비네이션 코에피션을 다 0으로 세팅하면 이건 언제나 true예요. 그게 우리가 그 전에 배웠던 트리비얼 솔루션이라고 불렀었고요.
예, 그게 트리비얼 솔루션 하나만 있는 거죠.
네, 트리비얼 솔루션이 하나가
맞아.
있고요.
네,
그다음엔
네.
이제 문제는 뭐냐면 그 0으로 모조리 다 대입해버린 그 어떤 가장 간단한 케이스 말고도 다른 솔루션이 과연 있을 거냐. 즉 어느 하나는 최소한 난제로를 세팅을 해갖고 이 식을 만족을 아니요. 벡터 v1, v2, vp는 여기서 주어진 거고요.
벡터.
네, v1들이 주어진 거예요. 근데
네.
주어진 거라는 거죠. 주어진 벡터들이고요. 거기에 붙는 이 그 가중치들, 스케일러 가중치인 x1, x2, 그 다음에 xp. 요 각각의 벡터에 붙은 그 가중치들 중에 최소한 한 놈은 난제로가 되어서 이 식이 만약에 만족이 된다면 그러면 이게 리니얼리 디펜던트하게 되는 경우고요. 거꾸로 그런 게 전혀 없어요. 즉 이걸 만족하려면 x1부터 xp까지 모조리 0을 대입했을 때 그거 딱 한 케이스만 이걸 만족하고 그 이외에는 어떤 케이스도 존재하지 않는다라고 하면 이 경우는 리니얼리 인디펜던트하다라고 보는 거죠.
그러니까 여기서 그러니까 벡터는 다 0이 아니고
벡터는 0일 수도 있고 0이 아닐 수도 있어요. 네, 그거는 그러니까 하여튼 모르지만 하여튼 무슨 벡터가 주어져 있어요. 벡터들이.
네네.
벡터들이 주어져 있고 걔네들에 붙는 이 가중치들을
이게 x가 무조건 0인 트리비얼 솔루션.
네, 그러니까 이게 무슨 벡터든 간에 x들에다가 다 0을 넣으면 우리는 이게 만족이 된다는 건 알아요.
네네.
그죠?
다른 게 안 된다는 거.
네, 그러니까 어떤 다른 경우도 그러니까 0 이외에 어떤 다른 경우도 존재하지 않다라고 하면 리니얼리 인디펜던트고 어떤 다른 경우가 존재한다. 그게 리니얼리 인디펜던트.
그럼 그 다른 경우가 지금 x가 이게 시험이
그렇죠. 네. 그러니까 not all zero라는 게 not always zero. 그러니까 이제 얘네들 중에 어느 한 놈은 최소한 이제 0이 아니면 그런 상태에서도 이 식이나 혹은 이 식을 만족하게 되면 그게 리니얼리 디펜던트라고 부르는 케이스 경우다 이거죠.
그럼 여기서는 무조건 x가 0만 됐을 때만 돼야 돼요.
네, 0만 됐을 때 그때만 이제 우리가 걔네들이 리니얼리 인디펜던트 벡터라고 부르는 거예요. 네.
근데 지금 저번 호모크 1 지금 거의 끝나가지고 풀이 넣고 있거든요 지금.
네.
일단 수요일까지 내겠다고 했는데 지금 많이 넣고 가지고 일단 오늘 낼 수 있으면 내고 일단 오늘도.
네.
출석 체크 다시 확인해도 돼요?
네, 이름이 뭐예요?
김유성 중에 언제 불렀죠? 출석 체크.
뭐 30분 정도 지나서 불렀던 것 같은데.
돌아서.
네. let's 보자. 여기 이름이 없으면 괜찮은 거예요. 네. 없죠?
네.
네. 그러면
감사합니다.
네.